Welcome to The Explainer. Today we're diving into the story of a particle that is so unbelievably small it seems, almost insignificant. But it's the architect of practically everything we see and touch. We're going to explore one of the fundamental building blocks of our entire universe, the electron.
I mean, just look at this. The immense, raw power of lightning. All of that incredible energy is unleashed by the movement of countless trillions of particles, and each one weighs almost nothing at all. It's a crazy paradox, isn't it, that something so powerful is driven by something so incredibly tiny? Well, this is the mystery of the electron. Okay, so to understand this particle, we've got to go way back in time. Long before we could even imagine something like a subatomic particle, people were noticing these first, faint little clues of an invisible force at play in the world all around us. It all started with a really simple observation. The ancient Greeks found that if you took a piece of amber and rubbed it with some fur, it would suddenly attract little things like feathers or bits of straw. Now, their word for amber was electron, and what they were seeing was the very first recorded experience with what we now call static electricity. Of course, they had absolutely no idea, but they had just stumbled upon the electron's calling card. For centuries, this was basically just a cool party trick. But then the scientific revolution kicked in, and people started connecting the dots. In 1600, William Gilbert gives it the name electrica. Then, in the early 1700s, Charles-François Dufay comes along and suggests there are two different electrical fluids. And finally, you have Benjamin Franklin in the 1740s, who simplifies it all down to one fluid, giving us the terms we still use today, positive and negative. So the idea was getting clearer, but the actual particle carrying that charge, still a complete mystery. All right, let's jump forward to the late 19th century. Things are about to get really interesting. Scientists were no longer satisfied with just describing this force. They wanted to find the thing that was actually carrying it. The hunt for the electron was officially on.
And the key breakthrough came from these things, high vacuum glass tubes. When scientists passed a really high voltage through them, they saw this mysterious beam, what they called a cathode ray, that would shoot from the negative end, the cathode, and make the far side of the tube glow. So the big question was, what was this beam? Was it a wave? Some kind of weird light? What was going on?
And this experiment gave them the answer. Scientists figured out they could actually bend these cathode rays with a magnet. Now that was the crucial clue. See, light isn't bent by a magnetic field, which proved these rays weren't light. No, they had to be a stream of actual particles, and those particles had to be carrying a negative charge. So, the big moment comes in 1897. A physicist named J.J. Thomson conducts a whole series of brilliant experiments and proves, without a doubt, that these cathode rays were made of unique, negatively charged particles. He called them corpuscles. A few years earlier, a guy named George Johnstone Stoney had suggested the name electron for the basic unit of charge, and pretty soon, that name was adopted for Thomson's new particle. The culprit had a name. But here's the part that truly shocked everyone. By measuring how much the rays bent, Thomson figured out the charge-to-mass ratio, and he realized these new particles were incredibly, unbelievably light. We're talking about 1,836 times less massive than a hydrogen atom, which was the lightest thing they knew. This wasn't just another atom, this was a tiny little piece of an atom. Science had just discovered the subatomic world. Just when scientists thought they had finally nailed it, the story takes a really, really strange turn. The electron, it turned out, was not the simple, tiny little billiard ball they had imagined. Not even close. Its true identity was way more bizarre, and it would end up rewriting the rules of physics.
So on the left, you've got the early, kind of intuitive idea, the Bohr model. It pictured the atom like a tiny solar system, right? With electrons orbiting the nucleus in these neat, predictable paths. Simple, makes sense, but it was wrong. The reality, which you see on the right, is what quantum mechanics revealed. Electrons don't have orbits at all. They exist in these fuzzy clouds of probability that we call orbitals. So we can't know exactly where an electron is, only the region where it's most likely to be. How is that even possible? Well, in 1924, a physicist named Louis de Broglie proposed this absolutely radical idea. He said, what if all matter, including our little electron, has a dual nature? What if it's both a particle and a wave at the exact same time? This mind-bending concept, wave-particle duality, is a cornerstone of quantum mechanics, and it's the key to the electron's weird behavior.
And this beautiful complexity here is what Erwin Schrödinger's famous wave equation describes. The answers to his equation don't give you a neat little path, they give you these beautiful, intricate probability maps. Every single shape you see is an orbital, a region where a bound electron could be. It's a fundamental limit of our universe. You can never, ever know an electron's exact location and its momentum at the same time.
So okay, the electron is this tiny, probabilistic wave particle. That might sound super abstract and strange, but this quantum weirdness is the single most important reason our world exists the way it does. So let's get to the big question. Why does any of this matter?
The crucial thing to get is this. Chemistry is basically just the story of electrons. That's it. The way an atom's electrons are arranged in those probability clouds, those orbitals, determines everything about how it behaves. When atoms share or transfer these outermost electrons, that's what creates chemical bonds. And those bonds hold atoms together to form molecules. Everything from the water you drink to the DNA inside your cells.
And once we figured out how to control electrons, we literally built the modern world. That simple flow of electrons through a wire, that's electricity. By learning how to precisely guide that flow through materials called semiconductors, we get all of modern electronics. We can even use focused beams of electrons for everything from welding metal to treating cancer, or we can even harness their wave-like nature to build microscopes so powerful we can see the building blocks of life itself.
So for this last part, let's zoom all the way out. I mean way out. Because the electron isn't just the architect of our world, its story is woven into the very fabric of the cosmos itself, right from the very first moments of time.
Here it is. In the standard model of particle physics, which is basically our best map of reality's fundamental ingredients, the electron belongs to a family of particles called leptons. And as far as our most powerful experiments can tell, it is truly elementary. It has no smaller parts inside of it. It isn't made of anything else. It simply is.
Its origin story begins in fire. In the very first moments after the Big Bang, the universe was so insanely hot and dense that pure energy could just spontaneously create pairs of electrons and their antimatter twins, positrons. For a short time, the entire cosmos was this churning, hot soup of particles being created and annihilated, just matter, antimatter, and light all in equilibrium.
So, from a strange little glow in a glass tube all the way back to the first seconds of the universe, the electron has been at the very heart of our quest to understand everything. It appears to be a truly fundamental, indivisible point of reality. But, every time we thought we had it figured out, a new, deeper mystery was revealed. And that kind of leaves us with one final thought. Is this story of discovery really over?